Greetings to the panel. My name is Suryaswaran Vijayandren and I am a final year civil engineering student. Today I will be presenting my findings on the research regarding the effect of driver's lane choice on the capacity of multilane roundabout using traffic simulation software. To start it off, I will first introduce you to the research topic and the problem statement. Then I will convey the main purpose and objectives of the research and a small summary of the literature review. I will then continue to describe the methods that I have used for this research and discuss the results that I have obtained. I'll finally conclude the presentation and give a few recommendations. Roundabouts were first introduced in the 1980s in places such as the UK and Australia. Here in Kuching, you can see roundabouts almost everywhere, especially multi-lane roundabouts that have large diameters. These roundabouts usually have an unequal number of entry and circulating lanes, and drivers who use these roundabouts will often need to make a choice on which entry lane should they use to enter the roundabout. The number of vehicles that a roundabout can hold at a time is the capacity of the roundabout, and it can be measured by counting how many vehicles enter the roundabout in a period of time. Large-scale capacities are usually calculated by capacity models like HCM and Kimber. These days, microscopic traffic simulation software such as VSIM have gained traction. Single-lane roundabouts are easy to use for drivers as they don't need to think twice on which lane they should use. However, when using a multi-lane roundabout, they do have to make a lane choice. People have also been observed to queue in the outer entry lane of a multi-lane roundabout due to a perceived ease. The effect of these real-life scenarios on the capacity of roundabout is not known, and capacity models today seldom consider real drivers' individual lane choice, and they use the default lane discipline instead. The main purpose of this research is to study the effect of driver's lane choice on the capacity of multi-lane roundabout using the traffic simulation software VSIM. The objectives are to identify the input parameters, validate the VSIM model using capacity results from a previous research of the same roundabout, and compare the effect of roundabout performance incorporating real driver's lane choice using VSIM on the capacity of the roundabout. Starting off with the literature review, these two figures show the recommended lane discipline by JKR. Left turns should use the outer entry lane, right and U-turns should use the inner entry lane, and through movements can use both. However, it was observed that a substantial number of people chose the lanes differently. Next, let's look at a few traffic softwares that are in use today. Rodel is an empirical regression model, and both Sidra and VSIM are analytical models that incorporate gap acceptance. However, VSIM has many more parameters such as car following and lane change behavior. VSIM is a microscopic simulation model that uses the car following driver behavior model that was developed by Wiedemann in 1974. It takes into account free driving, approaching, following, and braking modes. Its main features include link and connectors, routing decisions, priority rules, and reduced speed areas. For this research, the traffic flow data was taken from a previous research on a roundabout in the Kuching-Samarahan Expressway. The data has a morning and evening peak time. The roundabout has 3 circulating lanes, 3 legs that have 2 entry lanes, and 1 leg that has 3 entry lanes. VSIM 2022 was used for this research because of its capability to simulate driver behavior in a very microscopic way. 3 different types of models were made for this research. The first one is Standard Model 1, and it uses the default VSIM design, where there is only one connector. It connects the outer and inner entry lanes to the outer and middle circulating lanes. The figure in the bottom right shows the direction in which the vehicles will flow in this design. A few input parameters were inserted. Reduced speed areas were put before entering the roundabout so that vehicles will slow down. Desired speed decisions were inserted at approach and in the circulating lanes to control the speed range of the vehicles. Priority rule lines and conflict markers were inserted for each entry lane so that gap time values can be inserted. Data collection points were also inputted to measure the capacity of the roundabout. Standard Model 2 uses an alternate VSIM design. There is still only one connector, however, it connects the outer and inner entry lanes to the middle and inner circulating lanes, completely bypassing the outer circulating lane. This model was designed just to see the effect that it has on the roundabout capacity. The input parameters are also shown and they remain the same. The reality model is a model that incorporates real driver's lane choice. It uses two connectors. One connects the outer entry lane to the outer circulating lane, and the other connects both the outer and inner entry lanes to the middle and inner circulating lanes. In this design, left-turning vehicles will be routed to use the outer entry to outer circulating connector, and all the other movements will use the other connector. This is the closest it can be designed in terms of depicting real driver's lane choice in VSIM, as VSIM is not a lane-based simulation software. An additional conflict area parameter is shown, and it gives right-of-way to the vehicles going into the middle circulating lane. This is to avoid collisions. This is just an example of how Leg 2's 3-lane approach is designed. All three of the entry lanes connect to all three of the circulating lanes with just one connector. Here the identified input parameters are shown. The average standstill distance, which is the distance between two vehicles during saturated conditions, was chosen as 0.5 meters. The speed of vehicles when approaching the roundabout are 12 kilometers per hour, and the desired speed in the circulating lanes was chosen as 30 kilometers per hour. Next, the desired speeds for major and minor roads were chosen to be 60 and 30 kilometers per hour respectively. The desired speed at approach was set at 30 kilometers per hour. Suitable gap times were found for both the standard and reality models through a lengthy process of trial and error. The gap times were inserted in each lane in every model using the conflict markers. Through a process of trial and error, the gap times of each lane in the standard model 1 were calibrated for validation. The capacity values from the field data by Chong and Almamari 2020 were used to compare with the capacity values obtained from the standard model 1 in VSIM. If the VSIM capacity value is close to the field data capacity value, it would mean that the VSIM model is validated. As you can see from the two tables, standard model 1 is validated as VSIM capacity output values are close to the field data values. After the model was validated, the simulations were run using the traffic flow data and all three of the different models. The throughput capacity of each lane was measured using the data collection points that were shown before, and the data was tabulated and shown in a bar chart for comparison. From the charts of both morning and evening, it can be observed that the throughput capacity of almost every lane was reduced from the standard model 1 values when real driver's lane choice was incorporated in the model design. It can be affirmed that real driver's lane choice reduces the overall roundabout capacity, and this is probably due to an increased number of conflict points. When comparing standard model 1 and 2, standard model 2 severely reduced the overall capacity of the roundabout. This may be because in the design, the drivers are forced to cross multiple circulating flows, even the ones who just want to turn left. This increased conflict points. Due to the very low capacity output, standard model 2 can be said to be not adequate. Drivers in the reality model became more cautious due to the through, right, and U-turn movements using the middle and inner circulating lanes, as opposed to the drivers only entering into the outer and middle circulating lanes in standard model 1. Due to increased conflict points and being more cautious, drivers in the reality model became reluctant to enter the roundabout, thus reducing the capacity of the roundabout. In conclusion, the input parameters that were used in VSIM include reduced speed areas, desired speed decisions, average standstill distance, and gap times through the input of priority rules and conflict markers. The VSIM Standard Model 1 was successfully validated using capacity values from Chong and Al-Mamari 2020. When comparing the roundabout performance, it can be confirmed that real driver's lane choice reduced the roundabout capacity in VSIM. A few limitations and recommendations now. The traffic flow data used is from a previous study, so a new set of data should be taken. The occurrence of collisions during simulations is unavoidable since VSIM is a stochastic driver behavior model. VSIM is approach-based and not lane-based, so the input volume cannot be entered lane by lane. The very high number of input volume made it so that many vehicles were not able to enter the network during simulations. This would mean that the roundabout should be treated in the future to accommodate future population increase. Further studies on roundabouts with different number of entry, circulating, and exit lanes should be conducted so that their adequacy in VSIM can be known. Thank you.